when you force a 3-ton luxury chassis to sprint from 0 to 60 miles per hour in just 3 seconds. The laws of classical physics dictate that the structural metal must flex, and the suspension geometry should collapse under stress. To rewrite these thermodynamic parameters, the engineering architecture of the new Zeekr 9X completely discarded the standard laws of hybrid vehicle design. While legacy automotive brands are still struggling to implement basic 400-volt electronic systems into their alternative powertrain lineups, this vehicle features the world's first production plug-in hybrid architecture, operating on a full-stack AUKAS ultra-high voltage 900-volt system. This massive electrical leap directly solves the single greatest bottleneck in hybrid performance: transient voltage sag and internal resistance. In standard hybrid setups, demanding peak acceleration forces the high-voltage battery to drain through a volatile chemical matrix, generating catastrophic heat zones that compromise cell longevity. The Zeekr 9X counters this by utilizing a proprietary 70 kilowatt-hour lithium iron phosphate cell matrix capable of sustained S6C discharge rates. This 900-volt topology allows the electrical current to flow at significantly lower amperages while delivering higher energy density, permanently mitigating thermal buildup across the high-voltage bus bars. This ultra-high voltage architecture means the internal wiring harnesses can be reduced in diameter and weight, while simultaneously decreasing the energy lost as heat dissipation by over 50%. The current travels from the battery pack to the drive units through military-grade shielded high-voltage cables designed to withstand extreme electromagnetic interference, ensuring that even under maximum current draw, the electrical efficiency remains completely uncompromised. Connected to this high-voltage electrical heart is a tri-motor all-wheel drive powertrain engineered to humiliate traditional mechanical drive trains. Instead of relying on a physical drive shaft or heavy central transfer cases, the 9X splits its power across 3 independent permanent magnet synchronous motors, one dedicated to the front axle and 2 flanking the rear subframe. Working in unison with dual silicon carbide inverters that operate at 99.8% energy efficiency, this tri-motor configuration unleashes a brutal 1,281 brake horsepower and over 1,400 Newton-meters of continuous torque. The mechanical reality is terrifying. Transient torque delivery is computed in microseconds, executing rotational vectoring directly to the tires before a conventional mechanical differential could even initiate lockup. This setup allows for continuous, precise adjustments to individual wheel speeds, completely altering the vehicle's dynamic behavior during aggressive track maneuvers and ensuring absolute power delivery without mechanical lag. To prevent this massive tri-motor kinetic force from twisting the vehicle out of alignment during high-speed cornering, the chassis engineering team executed a complete mechanical purge of the traditional suspension assembly. In a standard luxury vehicle, body roll is managed by a passive steel anti-roll bar that mechanically links the left and right suspension arms. While this setup keeps the vehicle flat in flat corners, it introduces a severe dynamic compromise. A bump hit by the left tire forces a harsh mechanical shockwave through the solid steel bar directly into the right side of the chassis, completely destroying ride comfort. The Zeekr 9X completely eradicates this century-old mechanical dependency by introducing a high-frequency, 48-volt fully active anti-roll system combined with independent electromagnetic dampers. By splitting the front and rear anti-roll structures into independent segments controlled by high-torque electromechanical actuators, the suspension can decouple itself entirely during straight-line cruising. When the wheel encounters a severe road deformity, the actuator instantly rotates in reverse, neutralizing the vertical impact before it can travel into the passenger cabin. The internal hydraulic valving of the active dampers utilizes electromagnetic fluid that changes viscosity in less than 1 millisecond, shifting from a completely supple luxury setting to a rigid race car baseline instantaneously. This fluid contains microscopic magnetic particles that align when an electrical current is applied, creating an adaptive barrier that alters the mechanical dampening coefficient on the fly. the moment the vehicle enters a lateral G-force state during aggressive cornering. The 48-volt actuators apply up to 1,200 Newton-meters of counter-rotational torque directly to the suspension arms in less than 20 milliseconds. This proactive kinematic reflex completely eliminates body lean without stiffening the individual springs, creating a mechanical anomaly where a 3-ton chassis remains perfectly level to the horizon, while subjected to severe lateral load transfers. This predictive capability is further enhanced by an array of high-resolution stroke sensors located at each corner of the suspension, tracking suspension displacement and velocity to ensure the active anti-roll system counters force before the vehicle body can begin its rotational movement. Beneath the forward structural braces of the 9X sites an internal combustion engine that breaks every convention of traditional automotive propulsion. This is not a mechanical drive engine. It has no physical connection to the wheels. Instead, it operates strictly as an onboard, high-density thermodynamic power plant designed to feed the 900-volt high-voltage bus bars. By freeing the 2.0-liter turbocharged inline-4 engine from the variable rev demands of stop-and-go driving, engineers optimized its combustion geometry to achieve a world-first 46% thermal efficiency rating. In a standard luxury car, over 70% of the fuel's chemical energy is lost as parasitic heat through the exhaust manifold and cooling jackets, because the engine must constantly sweep across a broad RPM band. The 9X engine, however, runs strictly within a razor-thin, computer-controlled RPM sweet spot where the peak cylinder pressure perfectly balances fuel atomization. This engine utilizes an ultra-high 15.1 compression ratio, a high tumble intake port design, and an advanced Miller cycle valve timing strategy that maximizes the expansion stroke relative to the compression stroke. The electronic turbocharger features an independent electric motor mounted directly on the compressor shaft, allowing the system to force induction and optimize air-fuel ratios within milliseconds without waiting for exhaust gas velocity to build up. This active thermal management system keeps the internal engine components operating within their absolute thermodynamic optimum, minimizing friction and carbon deposition. When the onboard battery cells drop below a calculated state of charge, this dedicated power plant fires up to drive an integrated liquid-cooled generator. This system converts chemical fuel directly into stable direct current electrical energy at an unprecedented conversion rate, allowing the vehicle to sustain its full 1,281 horsepower output indefinitely, long after standard plug-in hybrids would have drained their batteries and defaulted to a sluggish low-power limp mode. The cooling jacket of the engine is interconnected with the cabin's thermal management loop, capturing waste heat from the exhaust stroke and recycling it to condition the battery pack during cold weather operations, ensuring zero energy wastage across the entire vehicle ecosystem. Unleashing this level of unyielding continuous acceleration and active suspension load force requires a structural foundation that goes far beyond traditional stamped sheet metal. For decades, Western luxury manufacturers have relied on standard high-strength steel alloys and riveted aluminum panels to build their premium monocoques. The structural engineering team behind the Zeekr 9X abandoned this compromise, developing an advanced metallurgical cage utilizing 2,000 megapascal hot-stamped boron steel across all primary load paths. To put this into perspective, this specific grade of ultra-high-density metallurgy is typically reserved for the construction of pressure hulls in deep-sea nuclear submarines to withstand catastrophic hydrostatic forces. This subsea-grade steel forms an absolute protective vault around the passenger cabin, specifically reinforcing the A-pillars, B-pillars, and the massive longitudinal sills that encase the battery pack. The manufacturing process involves heating the boron steel blanks to over 900 degrees Celsius inside automated multi-stage atmospheric furnaces, before stamping and rapidly quenching them within water-cooled dies. This extreme thermal treatment transforms the internal molecular structure of the metal into a hyperdense martensitic crystal lattice, yielding an unyielding shield that completely resists deformation during severe side impact collisions or high-velocity rollover scenarios. By implementing this ultra-high tensile metallurgy alongside an integrated, massive die-cast aluminum rear subframe, the 9X achieves a staggering static torsional rigidity rating of 41,600 Newton-meters per degree of deflection. The giant 7,200-ton Geiger press machines eliminate dozens of individual stamped components, welds, and rivets from the rear structure, creating a monolithic piece of metal that eliminates structural squeaks, fatigue cracks, and alignment drift. This immense structural stiffness ensures that the active suspension components are anchoring into an unyielding anvil of metal. When the vehicle encounters extreme lateral twists or violent road transitions, the body remains completely inert, preventing any microflexing that would degrade high-speed handling precision or create cabin vibration over time. The final mechanical frontier of the Zeekr 9X lies in its absolute decoupling of human steering inputs through a true steer-by-wire system, guided by the most aggressive sensory array ever fitted to a production chassis. The physical steering column has been entirely eliminated from the cabin floorboards. Turning the steering wheel sends encrypted digital signals across a high-speed, fault-tolerant bus to dual electromechanical actuators on the front steering rack, removing weight and allowing the steering ratio to adjust infinitely based on vehicle velocity. This eliminates the traditional feedback of mechanical road vibrations through the driver's hands, replacing it with an artificial force feedback motor that communicates tire slip angle and grip levels with surgical precision without physical fatigue. To guide this digital chassis safely through complex environments, the vehicle deploys a 5 LiDAR sensory matrix working in tandem with a dual NVIDIA Thor U processing platform, delivering an absolute computational capacity of 1,400 TOPS. While other premium manufacturers mount a single Dapash low-frequency LiDAR unit above the windscreen, the 9X utilizes a high-density 520-line primary LiDAR on the roofline, flanked by 4 solid-state LiDAR sensors seamlessly integrated into the wheel arches and lower body panels. This 5-point laser array creates an uninterrupted, high-frequency 3D point cloud map that blankets the vehicle's entire perimeter, scanning over 300 meters ahead even in total darkness or adverse weather conditions. Processing millions of data packets per second, the Vision Language Action System calculates spatial positioning with millimeter precision, mapping road anomalies, tracking moving obstacles, and actively feeding topography data back to the 48-volt suspension system. The mechanical steering rack features dual motor redundancy if the primary electric motor suffers a voltage spike or hardware failure. The secondary winding initializes within 500 microseconds to maintain absolute direction control. The old world of mechanical linkages, passive suspension components, and isolated internal combustion engines is completely obsolete. The era of high-voltage, 900-volt active hybrid engineering has arrived, and it is completely unyielding.